In this video, I am going to discuss about the equivalent definition of Riemann integrability, and also I will try to establish the equivalence of the basic definition of Riemann integrability along with this alternative definition. But before going through that proof, first of all, we have to remember some basic concepts which are associated to the concept of Riemann integration. So remember, in the class we have several times discussed about this fact. Suppose a function f is defined on a closed interval a comma b, then it is always possible to consider a partition of the form, say p, whose starting point a can be considered as x0 at the end point b can be considered as xn, and in between you can choose several points x1, x2, x3 dot 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 and so on. And also for our convenience we can assign the general point in this fashion, xr minus 1 comma xr. Now definitely it is going to be a partition of interval a comma b. Suppose here we are considering n plus 1 number of points, so definitely you can say altogether you have n number of sub intervals. With the help of this n plus 1 number of points you have created. Now if possible we are considering a certain sub interval ir. This is the generalized sub interval whose structure can be considered as xr minus 1 comma xr. Obviously length of this interval will be xr minus 1, that is final minus initial point, and you can choose any arbitrary points ir taken from ir. Now let us consider the sum corresponding to this particular partition point. So each and every interval contains a point like xir. So for the first interval I1 I am going to choose I1, for the second interval I2 I am going to choose I2, and so on. So let us consider n number of sub intervals, and we are defining a new sum that is given by summation f of xir into del r. So that's why you can see if I split this summation, it will look like f of xi1 into del 1, f of xi2 into del 2 dot 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 f of xin into del n. Now this particular summation will play a vital role while defining the alternative definition of Riemann integrability. So this is not the definition, this is just the basic concept or prerequisite which we require in order to define the equivalent definition. Now there is an important lemma, you can say. I have given the statement as well as the proof of that, which we have to consider here to understand the properties. So here you can see the statement says, if certain function f is bounded and integrable over the closed interval a comma b, then for every possible epsilon greater than 0 there corresponds a suitable delta greater than 0, which is valid for every possible partition like this, with the criteria norm p less equal delta. Now I hope you can remember the definition of norm, the largest possible subinterval which have the largest possible length. Let us consider that is equivalent to del. So norm p is less equal del. It indicates it may happen the subintervals are not of equal length, and if all possible subintervals are of uniform length, then we can say all of them have same structure. So here we can consider norm p less equal delta, as well as we can choose any arbitrary point xir taken from ir. Ir means xr minus 1 comma xr, and then we have to show summation of f of xir del r, what we have defined earlier, minus a to b fx dx within mod must be less than epsilon, and as usual del r refers to the length of the interval ir, that is xr minus 1. So to prove this one, first we can consider, since the function f is bounded and integrable, so definitely upper sum, lower sum, these two things should be identical and they should have a common value, that is a to b fx dx. Now remember, a to b upper bar fx dx, this can be considered as j, a lower bar to b fx dx, this can be considered as I, and a to b fx dx, this is the common value of the Riemann integral. So we can consider these three things must be identical because the function is bounded and integrable. Now we choose epsilon greater than 0, and in several theorems we have used the concept of Darboux theorem. So here we are also using the same thing. We can choose any arbitrary partition p for which norm p is less equal del, and we can use the Darboux theorem to state that UPF must be less than a to b upper bar fx dx plus epsilon. But because the function is integrable, so this a to b upper bar fx dx can be replaced by a to b fx dx plus epsilon. In a similar fashion we can also define LPF. Now what is LPF? A lower bar to b fx dx minus epsilon. That must be equivalent to what? A to b fx dx minus epsilon, because the function is integrable, that's why. Now as per our assumption, we have chosen the points ir from the generalized interval ir. So we can say between LPF and UPF we must have this summation, that is summation f of xir del r. Now remember, UPF is actually what? Summation capital M r del r, and LPF is actually what? Summation small mr del r, where small mr is what? That is nothing but the infimum of the function over IR, and capital MR represents the supremum of the function over IR. So whenever you are considering MR and small mr, any functional value should lie between these two. So that's why we can say small mr must be less equal f of xi r must be less equal capital MR. Now multiplying each of these quantities by del r and taking summation from r equals to 1 to n, you will get equation number 3. Now from this particular equation you can see, just using the definition of LPF, what can you write? A to b fx dx minus epsilon, because LPF is larger than this quantity, so definitely this part less than LPF, which is further less equal this part, which is less equal UPF, and UPF itself less than what? A to b fx dx plus epsilon. So combining all these possibilities, we can say A to b fx dx minus epsilon must be less than summation f of xi r del r, which in turn must be less than A to b fx dx plus epsilon. So you can see in the next page I have written the same thing. After considering all these conditions, we have this particular result. Now simply subtract A to b fx dx from each of these quantities, then you will get this part minus this. Here you will get minus epsilon, in the next part you will get plus epsilon. So just imagine minus epsilon less than something less than plus epsilon. So definitely we can put a mod over this expression. So mod of this entire expression must be less than epsilon as required. So in this result we are trying to prove, whenever we are choosing any arbitrary partition for a comma b closed interval with the criteria norm p is less equal del, then for any point xi r taken from IR, we must have this particular difference less than epsilon. That means if epsilon is very small, that is tending towards 0, these two things must be identical in terms of limiting sense. This is the main idea behind this result. Now here you can see I have given a note which is very important. What is that? Already the function f is bounded and integrable. It is already known to us. So whenever you are considering maximum number of points, that means theoretically you can choose infinitely many points. So as n tends to infinity, length of each subinterval becomes very smaller. So you can say length of norm p will be so small that it will tend towards 0. That means if you increase the number of partition points, gradually you can understand length of each subinterval will be very small. So that's why we can say limit norm p tends to 0, which is equivalent to limit n tending to infinity, summation f of xi r del r should exist, and it is nothing but the integral of f over a comma b, as you can see from this structure. Also let us define summation f of xi r del r for our convenience as SPF. In some books you can also find out this same thing is written in the form of SPF xi, because the point is taken under consideration here as xi. Now this part is what? xr minus 1 refers to the length of the rth interval. So that's why we can say summation f of xi r into del r. Now this particular sum SPF is also known as Riemann sum, corresponding to the function f over a comma b closed interval. So ultimately from relation 4, what can you say? A to b fx dx, which must be equal to what? This particular sum SPF in terms of limit. That means norm p tends to 0, but again norm p tends to 0 when this is possible, whenever limit n tends to infinity. That means if you increase the number of partition points, again I will say the length of the subinterval, whatever you have constructed in this fashion, should be smaller. That means you can consider in this type of structures, suppose we are considering the closed interval a comma b like this. Here we have several points. You can consider all these are partition points, but you can see how many subintervals you have created. This is the first one, this is the second one, this is the third one, this is the fourth one, this is the fifth one, and so on. Each of them have specific length. Now if I increase the number of partition points, then it will look like this. So you can see as I increase the number of partition points, length of each subinterval will be little bit congested or getting closer to each other. So theoretically you can increase the number of partition points up to infinity, and hence you can say in that case length of each subinterval will be very small. That means norm p will be tending towards 0. So norm p tending towards 0 is equivalent to the fact limit n tending to infinity. Now from this particular notation we have to arrive at the second possible definition of Riemann integrability. Now here you can see I have mentioned here in the second article the second definition of Riemann integrability, that is the definition: a function f is said to integrable over a comma b if there exists a number I refers to the integral of the function. For every epsilon greater than 0 there exists a suitable delta greater than 0, and that for every possible partition like this satisfying the criteria norm p less equal del with all possibles IR belonging to IR. All possibles IR belonging to IR means what? Xi1 taken from I1, Xi2 taken from I2, and so on, such that if you can show summation f of xi r into xr minus 1, that is summation f of xi r into del r minus I within mod must be less than epsilon, then we can say I is nothing but the integral corresponding to the function f with respect to the interval a comma b. So technically we can have this definition: this SPF is ultimately converging towards I, and obviously this situation will occur whenever we are considering the limiting sense. Now here again you can see note 2 I have given already. Note 1 I have explained what is the meaning of SPF. You can see the above definition can be restated whenever function is integrable and this particular sum is existing, and it should be independent of the choice of the interval. That means you can choose any interval IR, I1, I2, I3, whatever you want to say, and you can choose any point from it, and the definition is equally true for all possible intervals. And if we can have this inequality, then only we can say the structure or the summation part must be equal to I. I is nothing but the integral corresponding to the function f with respect to interval a comma b. Now here you can see as epsilon tends to 0, in limiting sense this part must be equal to I. So this is the alternative definition for Riemann integrability. Now we want to establish the equivalence of the basic definition of Riemann integrability as well as along with this alternative definition. That means you have to prove from the first definition you can derive the second one, as well as from the second definition of Riemann integrability you can also prove the first one. So let us try to prove that one now. Now in the next part you will see this article, proof of equivalence of two definition of Riemann integrability. Here you can see initially I have assumed that the function is Riemann integrable, so upper sum should be equal to lower sum, that must be equal to a to b fx dx. Here intentionally I have written this notation: a to b bar f, a lower bar to b f should be equal to a to b f. Now remember this part is known as j, this part is known as I, that means I equal to j because function is integrable. As usual you can choose the partition. Psi r is any arbitrary point taken from IR, supremum infimum corresponding to IR has been denoted by capital Mr and small mr, etc, etc. Now any functional value should lie between mr and capital Mr. That's why we have for all r we must have small mr less equal f of xi r less equal capital Mr. Multiplying all these expressions by del r and then taking summation from r equals to 1 to n, you will get this type of structure. But remember this is nothing but LPF, last part is nothing but UPF, and the intermediate portion is as per our construction nothing but sum function over partition P defined over F. That's why we can write this one as SPF. Now let us consider the norm P tends to 0, because already I told you whenever you are considering too many partition points, then definitely norm P will be so small that it will be considered as tending towards 0. So if we consider norm P tends to 0 and applying Darboch's theorem, then this part extreme left side will be converted into a lower bar to b f. This part will be norm P tends to 0 LPF, this part is equivalent to this one, norm P tends to 0 SPF, and this part will be what? Norm P tends to 0 UPF, and so this part is less equal a to b upper bar f. So in this fashion you can consider all possible inequalities. So because the function is Riemann integrable, so we must have a to b f less equal limit norm P tends to 0 SPF less equal a to b f. So ultimately you have limit SPF is equals to a to b f, which is equivalent to the integral I. So this is the first portion. So that means you have started from the formal definition and you have arrived as the alternative definition. Conversely, you can imagine that limit norm P tends to 0 SPF is equals to some quantity b. obviously this is a finite quantity. Consider the partition capital M r small m r as usual. Now let us consider epsilon greater than 0 be arbitrary, and there exists a point xi r taken from xr minus 1 comma xr. That means you are choosing the point from ir. Now f of xi r is definitely less equal what? Capital M r. Also let us choose another quantity which is smaller than capital M r. That is, it is always possible to choose a functional height lying between m r and obviously some quantity which is less than m r. Here I have taken m r minus epsilon by b minus a. Why? Because you can imagine the length of the total interval is what? B minus a. That's why I have taken the quantity is like this, m r minus epsilon by b minus a. Now operate del r on either side. Del r means xr minus 1. So m r into this, epsilon by b minus a into this, f of xi r into this, capital M r into this. Apply summation r equals to 1 to n over each of these quantities. Now this part is what? Capital M r del r, that is UPF. This part is less than what? Epsilon. So ultimately UPF minus epsilon you can say, because this part whenever you are putting 1 to n, ultimately you will get x1 minus x0, x2 minus x1, x3 minus x2 and so on. After adding all these quantities you will get it is also equal to b minus a. So b minus a will be cancelled, so that you will get only epsilon will survive. So this part is UPF minus epsilon. In the mean portion you will get what? SPF as per our definition. Remember I told you, because we have taken the point xi under consideration, so we can write this one as what? SPF xi, and the last part is what? Nothing but UPF. Here you can see, if I put r is equals to 1, the first part will be like this, second part will be like this, third part will be like this. So you can see x2 will be cancelled, x1 will be cancelled and so on. So finally we can get xn minus 1. If you add all these quantities you will get xn minus x0, which is b minus a. So this part under summation gives you b minus a will be cancelled. So finally we have obtained this type of relation, UPF minus epsilon less than SPF xi less equal UPF. Apply norm p tends to 0, then you will get this type of relation. Now this part is what? Under limiting sense a to b upper bar f minus epsilon. This part as per our assumption b, because remember we have already mentioned this thing, limit SPF is equals to b, and this part is also UPF. So this portion less equal b less than a to b bar f, which is further less than a to b bar f plus epsilon. So forget about this quantity, this less equal b less than this portion. Ultimately you can say b minus a to b bar f must be less than epsilon. But because f is assumed to be like this type of structure, that means b epsilon is very small, epsilon tending towards 0. So you can say b, if it satisfies this type of structure, must be identical to a to b bar f. This is equation 2. Now we have to do the same thing in terms of small mr. That means let us choose another point xi r dash taken from ir. Now small mr less equal f of xi r dash less than mr plus epsilon by b minus a. I hope you can remember in the previous case I have taken capital mr minus epsilon by b minus a. Now I am choosing a quantity which is larger than small mr. Again apply del r on either side, that means xr minus 1, and you can also operate summation r is equals to 1 to n, so that you will get LPF less equal SPF xi dash less than what? Ultimately LPF plus epsilon. Now consider limit norm p tends to 0, then you will get norm p tends to 0, norm p tends to 0, norm p tends to 0. But limit norm p tends to 0, LPF is what? L over bar to PF. This part will be less equal like this, this part will be less equal L over bar to BF plus epsilon. So you can imagine this part is larger than this quantity a lower bar to b f minus epsilon, which is less than this, which is further less equal b, which is less equal this. So forget about this portion, this less than b or less equal b less than or equal this portion. So again you can write b minus a lower bar to bf must be less than epsilon. The only possibility from here you will get b should be equal to this quantity. So that means you have two possibilities from the previous equation as well as from this equation. From 2 and 3 we will get b is equals to a lower bar to bf, and that is equal to a to b upper bar f, and hence you can say if these two things are same, that means this is I, this is j. That means you have obtained b is equals to I equals to j. So the function must be Riemann integrable. That means this establishes the equivalence of the two possible definitions of Riemann integrability. This is the required proof. Thank you.